Right. So first up, the energy balance. So the assumption when I give these lectures are that you watch the video. So it's not just a summary of the videos. I want to relate to the previous material and current other subjects that you may be busy with in the energy balance, and some hints on the TAT today, and address some questions that I've received over Slack or email. So if we consider the energy balance for any steady state flow process. So what you are going to do in your course with Mike is you are going to have a course where you are going to do energy balances in some simulation software, like I'm not sure what you're going to be using, DWSim, or whether you are going to be using Aspen, and you're going to have stuff coming into your reactor and you're going to have stuff going out, and you're going to specify, is it a Gibbs reactor? A Gibbs reactor means it goes to equilibrium, or you're going to specify a specific reaction that takes place, and you're going to specify conversion. And how does Aspen then do your energy balance? What it does is it considers the enthalpy of everything that comes in and the enthalpy of everything that goes out. And it's not going to use this Dow enthalpy approach that we are using, because it's got a database of lots of values like steam tables. So it can find for all your, let's say you've got A that's going plus B that's going to be converted to C. So it's going to say, what is my state at the inlet? What's the temperature? What's the pressure? And therefore, what's the enthalpy of A at that point? What's the molar flow rate of A? And then it can calculate, and it can go and read it up from tables and from all its databases. It can calculate the inlet enthalpy of the inlet flowing stream. And similarly, if you specify a specific conversion linked to a reaction, it can calculate your outlet product spread. So it will know how your flow rates look out, and it will then do an energy balance. If you tell the system it must be adiabatic, you specify Q to be 0, and it is going to trial and error then for the outlet temperature, T out, by calculating H values, looking them up in a table and calculating so it's going to use the H in sum of all H's in minus sum of all H's out must then be equal to 0. And this is the kind of energy balance that you will get from Aspen. If you say, I don't want it to be adiabatic, so there must be some heat flowing, so Q, and you then specify the outlet temperature. What Aspen or DWSim will do is it is going to calculate at the specified inlet state, at the specified outlet state, what's the enthalpies, and therefore what is your Q value going to be in kilowatts from that reactor. That's the kind of energy balances you're going to do when you start modeling your designs in your design project, or even I think maybe this semester in Mike Heidenreich's subject. So what we are doing is in fact the CTD approach. So this relates to your CTD pre-knowledge, okay, where we said, okay, we know that our energy balance is 0, left-hand side, because we're at steady state, equal to Q. We are going to neglect all work terms. So all shaft work terms negligible. We're not driving turbines or pistons or whatever, plus energy that's in with mass, and we are only going to consider enthalpy, energy leaving. So our energy balance at this stage looked exactly the same as the Aspen energy balance. So this is out. But this we are now going to write as a min del H of our flowing streams, and that is either, so del H is either equal to Q or 0. And for the purposes of today's content, it is equal to 0. And that is where we are now. So why I focus on this lecture is I notice some people still want to have the del H of the reaction somewhere else. They want an extra space for del H of the reaction. It is not an extra special term. It is part of the change in enthalpy of the flowing streams. The enthalpy of the flowing streams changes because of the reaction, because of the bond energies, and because there's a change in temperature. Right. So don't think about the heat of reaction. Heat of reaction, that's why, you know, it's the word that we use, which may actually be a misnomer, as energy that's being added or energy that's being removed. It is a change in energies of your components because of different bond energies that shifted, and therefore it results in a change in internal energy, which we see in a change in enthalpy. Right, so don't go looking for an extra term for the del H of the reaction. The del H of the reaction is in there, and that is in those steps that we choose our convenient path. So we choose the delta H path. What Aspen cannot do for you is if you have to design a reactor. Aspen cannot design a reactor, and by designing it means sizing it. And now at this stage, I hope you realize that sizing a reactor, designing a reactor, is much more than just specifying the volume or the amount of catalyst. You must also specify the layout in the case of a PBR reactor. And how you lay it out, hopefully in the online test, you can see that that affects the pressure drop in your reactor if you've got a gas phase reactor, and the pressure drop affects the performance. So it's designing a reactor is much more than just specifying a volume or a mass of catalyst. It is also your job to say, how must that thing look? How must it look? How much area must be available for heat transfer? So this is the first part, is to say, right, this is the amount of catalyst, this is the volume, and then fine-tune, trial and error. Design is always a trial and error, or not trial and error, because you will not be making any errors. But it is an iterative process. So you will first get just a mass, and then you will say, all right, how am I going to distribute it in tubes? Is it going to be in a CSTR? Or of course, you're going to decide on your type of reactor first, CSTR, PBR, PFR, and then you can now finally start your design process. After you've got an initial mass or volume, say, okay, now I'm going to distribute it in 200 tubes. This is the length. So lots of design decisions that you must make in the process. Okay, right. But in the TUTs, we slowly make you used to it. So in this week's TUT, I want to share some content. The CSTR, some comments on the notes that I made. We just share some files, hang on, to adiabatic, there we go. Right, so I actually want to go to a different slide. Sorry. The slide where I show you the application in Python. Yes, application in Python. So hopefully you are all familiar with this video, or you went through the slides, depending on how your learning preferences, looking or listening. So this is where I showed you an example of the mole balance, just the graphical solution. So you get an idea of what happens in a CSTR with a single reaction. Is that this is the solution we are after, and once we have a graphical solution, it is very easy to apply that in fsolve. So it's very easy because in fsolve, I've got a love-hate relationship with fsolve, and I'm sure many of you will have the same kind of relationship before the end of the semester, because it works and then sometimes it doesn't work and it doesn't even tell you that it's not working. So I've since figured out how I can get it to tell me that it's not working. If you want my secrets, I will share it with you. But what we discussed in our TUT meeting yesterday, and Gabby reminded me that I may actually be leading you along the wrong track. So thank you for that, Gabby. It's easy in fsolve if you have to guess two initial variables. So this means if I want to solve, if my variables that I want to guess, I have to have two equations that must be equal to 0 to solve them. Right? But what you must realize, when we solve these mole balances, so let's just, if I write the two balances, FA minus FA naught plus RA times V, and here I've got my energy balance, I don't have to rewrite. Here I've got it there. I actually have much more than just those two unknowns there. Many more. I've got FA right? I've got RA, okay, the volume was specified in this case, and in RA I've got CA, that's a variable, and in my RA equation I've got K, so I actually have gazillions of variables, and if I want to, I can for each one write an equation. I can say, okay, CA is going to be FA over Q, so I make CA an additional variable and now I have to return an equation here that will look like CA minus FA over Q. And I want the rate to be a variable that I solve for, so let me add the rate. And now I have to return an equation that says RA K minus whatever, that whole non-linear equation. So there are many more variables. I've just reduced it to guess for 2 to help fsolve. The problem with increasing, let me just get some clarity here. The problem with increasing the amount of variables that you have return equations for is that you have to supply the first guess. And for some of the very non-linear systems, as you've seen with that, or you will hopefully see with that 2.1, if you increase, so that looks like that. If you get it correct, you will get something like that. Where your first guess is going to determine your solution, right? So now picture, I didn't draw that graph. So this is now the example I show in the on this slide. Let's say I guess a conversion of 50%, and there. Say, fsolve, please start there. The chances are, if it's very nonlinear equations, that it may not even find a solution. It's just going to return your initial guess values. If you've got, have you run into that problem with fsolve previously? It just returns your initial freaking guess values. Thank you very much for that. Okay, so it is because it's not for this problem, and sometimes you don't have the luxury of being able to plot the equation so that you can find the solution. So a suggestion here is to do the following. So once you've done with your TATs, please try the following, right? It solves it much. You make fsolve's life easier by doing this. So I am not going to have temperature here. So let me just have a red. I'm not going to have temperature here as a variable. I am just going to guess for X. And I know where to guess X. At least I've got a very narrow range for guessing X. It's between 0 and 1. Okay. Now, instead of returning my energy balance, I am still solving for those two equations. But instead of returning that energy balance over there, I am going to use algebraic equations to, okay, now you've guessed X, I can calculate FA, I can calculate epsilon, I can calculate RA, I can calculate that. But okay, so no, I can't calculate RA because I need to calculate the temperature first. Is instead of returning the energy balance like this, where it's equal to 0, do some algebra and make that temperature the subject of your equation. So once you have, now it's going to fit in there, sorry. Once you have guessed an X value, you can calculate an FA, you can calculate an epsilon. And then you can make temperature the subject of that energy balance and use an algebraic equation there to calculate temperature and then your rate. At least what it does is if you guess an X value, it finds a T value that's more realistic. Right. So you help fsolve to solve your equations. It's almost like if you have to design your own fixed point iteration loop. How will you do it? You will not guess an xt simultaneously. You will guess an x and you will calculate the corresponding temperature and then see whether that results in a solution. So that just makes it easier to find. If I guess a 0.5, I don't also have to specify a temperature. Right, so for your solution procedures, try that. Okay, so I know in the graphical approach, if I have a solution, so all I'm doing is I'm guessing, it must be about 90% and the temperature must be about 620, and bee's knees, it's going to be very easy to solve that. fsolve is not going to struggle, right? But if you now don't have the luxury of a graphical solution like over here, you may end up guessing yourself into doom. Okay, into that height part of the relationship with fsolve. And we are going to do lots of subsequent theory where we have even more nonlinear equations where I want you to keep that in mind. I can write it in terms of a gazillion equations that I return over here, and I then have to have a gazillion first guess values, and they need to be good. Right, okay, good. Do I have any questions on this? From the floor or from online? Okay, right, and then I also want to, okay, let me just give a few seconds for the online people to raise hands. Raise hands if you're online and you've got a question and you want to type. In terms of the adiabatic plug flow reactor, so let me just go back, share the plug flow reactor, hang on. I also want to make some comments here, because I see some people are struggling with that. Not this slide. This one. The application in Python. So you can zoom in and zoom out. So what I often ask people to remind themselves of is independent variables when you solve these equations. So let's now say I chose as my independent variable the volume, and I have now written a few differential equations. What you must realize is, once again, I actually have quite a few dependent variables. So if I inspect my mole balance and my energy balance, in my rate equation, I have the rate, that is a dependent variable. I have my K value, that's a dependent variable. I have my concentration, that's a dependent variable. I have the volumetric flow rate, that's a dependent variable. And I can add here variables that I want to return differential equations for. So for each of the, so what I mean by variables is the ones that I'm going to feed into my differential equation function, independent variable and variables for which I am going to return differential equations. I noticed that you are used to, or you want to do some math, nothing wrong with it, to add Q here and to return a differential equation for Q. Be careful. No? If I use the ideal gas law for Q, and I explain it in some of the videos, but I want to stress it because people seem to miss what I want to say. NRT, ideal gas law suddenly. Right. If I want to see how this thing changes with volume, this is a function of volume. This is a function of volume. This is going to vary with volume. So then you have to just, it's like I've got an f of x, I've got a g of x, and I've got an h of x. And I want to determine this function dx, dfx, dx. So go back to your maths. It's nothing scary. You should be able to do it if you want to do it, but just take cognizance of that fact. So for all my other variables for which I don't return differential equations, I use algebraic equations in my function. So I prefer for Q to just use the ideal gas law, and I can, after my function, calculate Q when I know these variables. I just calculate it in an array then. I'm not sure whether I'm making any sense at all. Ask me if there's no clarity here. Variables, you have many more than the few that I've just shown here being variables. You have lots. This is just the variables for which I return differential equations. For the rest of the variables, I still need equations. My degrees of freedom must still be equal to 0. Okay, sorry, I'm talking to the crowd and not on screen. My degrees of freedom must still be equal to 0. My degrees of freedom must still be equal to 0. And I must therefore match the number of differential equations and algebraic equations with the amount of true variables that I have. So sorry if this confused you. Okay, last thing that I want to discuss, and this is now getting into the why we are doing this, or the implications of what we are doing. There we go. Sorry, it just takes a while to swap between slides here. There. So I want to discuss this question that I asked on the slides. So right, how does the Levensspiegel plot look? for when I've got an adiabatic exothermic reaction or when I've got an adiabatic endothermic reaction. And I don't want you to guess this. So it's, we don't have to guess. You've got your own labs. You've got your labs there in front of you at your fingertips. I want you for either TUT 2.1 or TUT 2.2 with the right detail given. Construct a Levenspiel plot. You can decide at which point you feel, okay, I'm up for it, I want to construct a Levenspiel plot. What you need to get rid of, the paradigm that you need to get rid of, is that the Levenspiel plot is associated with a specific reactor type. It is not. It is a function of what is my initial concentration that I've got available, where do I start, therefore how fast can I start. Okay, and it is a function of your rate expression. So my recommendation is when you construct a Levenspiel plot, go back to your TUT1, have your X range of values. Okay, for each X, I can now use my energy balance to calculate a temperature. And for each X, I can calculate an FA. And for each FA, I can calculate a concentration. Right. And therefore, for each X, I can finally calculate my rate and I can construct my Levenspiel plot. Right. I want you to draw this plot, and halfway through the lecture, I will, once you've drawn it, just get my attention so that I can see. So don't start the TUT with that. You need to have some, get some meat on your TUTs first. Oops, daisy. We are going to pause in the middle of the lecture to discuss the shape of the Levenspiel plot. What I also want you to do is in TUT 2.1 and TUT 2.2, both of them are exothermic. So del H of your reaction is negative, right? Just for the sake of this exercise, change the sign of del H reaction and see what happens to your Levenspiel plot. And think about what you are seeing. Critically think about your answers. This is the one thing that I want to teach you, is not just to accept the answers you get. That what happens then is you get a pressure drop of 500 kilopascals per kilogram of catalyst and you don't think about it. You don't think whether that's realistic. That's half a megapascal pressure drop, right? And I realize at this stage you are just so glad that you get an answer, okay? That you don't care about what the answer is. So I had students who did the most amazing designs last year in their final year research project. And then they want to treat 26 tons per second of product, and the reactor is the size of my pressure cooker that I have at home. No? And the code worked, everything worked, it looked fantastic, but it's not realistic. So something must be wrong with units or something else somewhere. So critically start to think about what you're seeing. Why is the PFR better here? Why is the CSTR better? Can I explain it? Right, so that is it. That's what I want to tell you today. I hope you have fun with the TUTs. I am going to be taken off grid this weekend by my family. So they are taking me away where I will not have a device with a signal. So I am not going to be able to respond to any, I apparently won't even have electricity. So I will not be able to take care of your queries this weekend. So ask in your groups, but I'm not ignoring you. I'm not in a position to answer. I will hopefully be back on Monday. Right, so I am going to